after I'm done saying what I want to say about kinetics, if anyone has any questions about practice problems or anything, then let's do that after. But let me just finish what I was going to say about kinetics first. So last time, so here's basically how this is going to go. Last time I gave you this problem. Okay, wait. Exam 3 is tomorrow. At 7:24. And the topics are rigid body kinematics and rigid body kinetics. Okay, and then last time we did a problem where you had a board. This angle was 30 degrees. The center of mass of this rectangular object is right in the middle of the rectangle. And halfway between the center of mass and the end point was a pin. And so that pin is fixed on the board, and it's also fixed in our inertial coordinate system. So we can use this as the about point. And then we had a 100 Newton force going this way. And we wanted to find, oh, let's see, what do we know else? We know the lengths. It's 1 meter long, 0.2 meters wide. The mass was 30 kilograms. This is a view from above, so we didn't have to worry about the weight or the normal force. Those are both out of this plane. And we just wanted to calculate the angular acceleration. And so the way we did it last time is we made the about point for, no, sorry, the rotational Newton second law. At the pin. We could do that because it's a fixed point, and went through all the work, and we got that the angular acceleration was equal to 0, 0, negative 11.17 radians per second squared. And we used a rotated coordinate system. Our coordinate system was like this. It just made the calculations a little bit easier. But notice that for our final answer, this angular acceleration is in the z direction. And so this is the same answer that we would have gotten in this, right? That vector doesn't change if you rotate the coordinate system about z. Okay. So now we're going to do this again. But we're going to do it with the about point at the center of mass. We can do that because we can always make the about point the center of mass. The one that we can't always do is the about point at a fixed point because we don't always have one. How would you guess the angular acceleration that we get this way should compare to this angular acceleration? Should be the same. That's right, because it's the same thing. Otherwise, one of these two ways doesn't work. Okay, so this is always a way to sort of check your answers when you have a fixed point. Okay. what we're going to see is that when you have a fixed point, you're a lot better off taking advantage of it. A lot of extra steps go into this. And after I'm done doing this, then I'll step back and give you kind of a step-by-step approach for doing these kinetics problems. Okay. So first, let's calculate the moment of inertia. We know that's going to come up in rotational Newton's second law. It's a rectangular shape. Is it spinning like a blade or like a paddle wheel? Blade. And so the formula is 1/12 times the mass times the height squared plus the length squared. So 1 squared plus 0.2 squared. And yes, 2.6 kilogram meter squared. We got that on the way to getting our moment of inertia for the last one, but then we had to use the parallel axis theorem to move it to that fixed point. This time, this is the one we're going to use. And now we'll go to the free body diagram. And this is where the wheels start to come off. Well, the wheels don't come off, they just start moving really slowly or something. So what are the forces? There's the 100 Newton force there. And there's one other force at the pin, yep. So I'll call that FP. And now I'm going to write out the table and we're going to start going through this. So pancake, artists, row, 4, marzipan. Put the origin, I guess I put the origin at the center of mass. So the forces, how do you get from this point to this one? Well, you know that this angle is 60, so you know this angle is 30. And so this angle has to be 60. And you know the distance between these two is 0.25. So from the origin to here is 0.25 times cosine of 60, 0.25 times sine of 60. And so 0.125, 0.2170. The about point is the origin. Subtract to get the row vector. The force vector is FPX, FPY, 0. And now take that cross product. This is all happening in the XY plane, so the only non-zero component is going to be Z. And we get 0.125 FPY minus 0.217 FPX. And that's in the Z direction. And the next force is where this 100 Newton is applied. Notice the line of action goes right through this center point that's 0.25 meters away. So I'm just going to assume that that force is there. That's equipolant. So that vector is going to be, well, negative of this, you know. Just take the vector we just had and multiply it by -1 to flip the direction. And so we have -0.125 negative 0.2170. The about point can't change.
Why are you changing the direction?
Well, this is now representing the coordinates of this point. So
Where the force is being applied to?
this is the origin here. And so the coordinates of this is this, the
The center mass too.
yes, yep.
So
It doesn't have to be at the center mass, but I just put it there.
Doing it, so now you want it on the spot where the force is being exerted.
Right, yep, that's right.
So the pin and 100 Newton force are the same distance away.
Yes, that's right.
Yeah.
And they're both along that same line. And this force vector, well, let's see. What's that angle? So the way I said to think about this last, like a week ago in statics, is start at the positive x-axis, rotate 60 degrees, and now you're there. This is perpendicular to it, so rotate another 90 degrees, and now you're in the direction of that force, and you get 150. Okay, so if you think of just always adding up angles to get to the angle you want to be at, you can always use that angle with cosine and sine to get the vector. So that's 100 times cosine of 150, 100 times sine of 150, which is negative 86.650, 0. And can anyone do that cross product in their head? Well, if you also think of it as this is a perpendicular force to a moment arm of 0.25, that just has to be 25 Newton meters. But that's what you get if you do the cross product there. And is it going to be positive or negative? Negative. You can eyeball that because that would cause a clockwise rotation about the about point, the center of mass. So negative 25z. All right, so now what did we do at this point in the other method? Do you remember?
How do you know which way it's rotating? Like, how do you know what to
Well, just picture, so once you choose your about point, this time our about point was the center of mass. Imagine, even though there's not physically a pin there, imagine there being a pin or a hinge there. Would that force make it rotate clockwise or counterclockwise? Okay, yep. So what we did with the other approach at this point is we went right to the rotational Newton's second law, and we solved for alpha, and we were done. We can't do that here because we have something that appears in the rotational equation this time that didn't the last time, and that's these unknown forces Fp. Okay, those unknown reactions at the pin. When your about point is the pin, those forces always disappear in the moment equation. And that's kind of at the heart of what makes it simpler to use the fixed point as the about point if you can. Now that we're not using the about point, those appear, they do produce a moment. And so we have to deal with those. And what that means is now we can't just use the rotational equation. We have to use Newton's second law also. So Newton's second law says Fpx, Fpy. I'll leave out the z's for this because that just is going to give us 0 equals 0. Plus negative 86.6, positive 50 is equal to, well, what's it equal to? Now more variables come up. It's equal to the mass times an unknown acceleration of the center of mass. Okay, so 30 kilograms times A COM X, A COM Y. Okay. And the rotational equation says negative 0.217 FPX. Like the only non-zero component for this equation is the z component, so I'm leaving off the other two. But negative 0.217 FPX plus 0.125 FPY is equal to the moment of inertia, 2.6, times alpha.
Don't shoot me down. I'm thinking 25.
Ah, yeah, I forgot that. Thank you. Minus 25. What's so 2.6 alpha. So yeah, you're just taking, just like we did in statics, add up all of these. Those go over to the left-hand side of Newton's second law. Add up all of these. Those go over to the left-hand side of the rotational equation. And so before we had one equation to solve. Now we have three equations. That's bad enough. But now look at this. Three equations. 1, 2, 3, 4, 5 variables. Okay, so what do we have to do? I mean, it's really the same thing we always have to do when we have more variables than equations. We have to come up with some kind of geometric constraint. So what else do we know that isn't appearing in this yet? Yeah, that's right. That's how we're going to get it. And what we know physically is that this point P, the pin, has zero acceleration. It can't go anywhere, right? And so we need two constraint equations. And we'll get those by requiring the acceleration at the pin to be equal to 0. Okay, so we want to represent the acceleration at the pin without adding any new variables, otherwise it doesn't help us. So in terms of the variables that we have, here's what we have. We have the acceleration of the center of mass, the angular acceleration. This isn't a variable, but at the start of the problem, we're given an angular velocity. I didn't write that down, but at the start of this problem, I said omega is negative 15 radians per second. And then we have FP, and I guess that's all. So notice that the acceleration of the pin is equal to okay, think of it this way. The acceleration of the pin relative to the ground is equal to the acceleration of the pin relative to the center of mass plus the acceleration of the center of mass relative to the ground. Okay. This is the ACOM that we already have represented. This is 0. And this is the watermelon equation. Alpha cross R plus omega cross R.
By when you're saying pin in here, that's whatever you assign to be the pin. Or are you talking about point P in this situation?
The point P, like the actual pin, yeah. Like, because we know that that point's fixed. So that's the only point where we know beforehand the acceleration. We know that it has to be equal to 0. So, yep.
I thought the whole point of doing this was doing it when you don't have point that's fixed.
When you, that is usually why you have to do it. In this case, we're doing it to check our work from the other method. And so,
if we had no given fixed point.
right, if you didn't have that, then, well, you wouldn't have that unknown reaction force.
Right.
So you wouldn't have to, so we'd be able to have just solved it on the last page. Okay, so the acceleration of the pin relative to the center of mass is 0, 0 alpha crossed with, what's the R that we want? It needs to go from the about point for, so right now, to calculate the acceleration of the pin relative to the center of mass, just for this part, we're assuming that the center of mass is what's fixed, and we're only worrying about the rotations around it. Okay? So we're going to assume that the center of mass, what?
The center of mass is the inertial perspective, but the pin is still fixed.
The pin is really physically fixed.
Yeah.
But when we're doing this relative motion stuff, at each step, there's something that you're assuming is fixed. You know, that is whatever is
So for me, just
in the
my
bottom, the
I
denominator.
see it rotating around the pin, but the center of mass is still moving. So I don't see that.
The center of mass, that's right, the center of mass is moving, but when we're calculating the acceleration of the pin relative to the center of mass, for that relative to the center of mass means, for a second, let's assume the center of mass is fixed and figure out how the other stuff rotates around it. Okay, so R is from the center of mass to the pin. So that's the same as this vector. So 0.125, 0.2070. Omega is given is 0, 0, negative 15. 0, 0, negative 15. Cross with R. And if you do all that, you get negative, oh, it's not 0.207, it's 0.217, sorry about that. But if you do all these cross products, you get negative 0.217 alpha, 0.125 alpha, plus negative 28.125, negative 48, 0.825. So now we're going to take this, put it back into this relative motion equation, and we get that 0, 0 is equal to negative 0.217 alpha, positive 0.125 alpha, plus negative 28.125, negative 48.825, plus a COMX, a COMY. And there's our two extra equations without adding any extra variables. And now we have a system we can solve. So if you put this, so if you set this up as a matrix equation, we have 5 variables, 5 equations, so we need 6 columns and 5 rows. Here's equation 1, 2, 3, 4, 5. This is FPX, FPY, ACOMX, ACOMY, alpha, and the constant. And you get 1, 0, negative 30, 0, 0, 86.6, and then 0, 1, 0, negative 30, 0, negative 50, then negative 0.217, positive 0.125, 0, 0, negative 2.6, 25. And then the last two equations, 0, 0, 1, 0, negative 0.217, 28.125, and then 0, 0, 0, 1, 0.125, and 48.825. Okay, and now use RF on that, and you get that FP is equal to 857.66, 1456.63. We didn't find that out the other method, but we didn't have to for what we were looking for. The acceleration of the center of mass is 25.7, 50.22 meters per second squared. We didn't find that out last time, but we didn't have to. And then alpha is equal to negative 11.67 radians per second squared. So we get the same thing again. The alpha vector is 0, 0, negative 11.67 radians per second squared. So the moral of this story is you can always use the center of mass you can use the center of mass as your about point when you have a fixed point. But don't. Yeah.
If it's not implied verbally that something's rotating about a point, can you assume that it's rotating about its center of mass? Like the boomerang.
Like what?
Like the boomerang.
Oh,
What would you do
well,
at that point? Or
I mean, I guess in a way you could say, it's rotating about any point you want. As long as its orientation is changing, you could imagine it as a translation of a point that's not even on the body and a rotation about that body. You could always break it down that way, but it never does you any good to think of it as a rotation about anything but the center of mass. And the reason is that we have equations for calculating the acceleration of the center of mass, but we don't for any other points. So yeah, it's you always either want to think of it as rotating about a fixed point or rotating about a center of mass at the same time that the center of mass is moving.
Can you put it back on that,
And so, by the way, this is kind of, the next topic we're going to get into is linkages. In linkages, you're going to have all these variables floating around. Like each body, you're going to be dealing with the acceleration of its center of mass and its acceleration. And the way that you're going to apply the geometric constraints, because if these things are connected at a pin joint and moving, your geometric constraint has to say that they're moving in such a way that those 2 points stay together. You're going to apply those by using the watermelon equation from this body to represent this point, and using the watermelon equation from this body to represent this point, and saying they have to be equal. So that's where all those constraints are going to come from. It's horribly tedious, Okay, so let's go through a set of steps for doing rigid body kinetics problems. You don't have to follow these, but it does sort of make sure that it's a way of just kind of making sure that you don't miss any steps, forget to do anything that you have to do. Okay, so the first thing you have to do when you know you have a rigid body kinetics problem is you have to figure out, is it rotating about a fixed point or not? And that fixed point, it's not enough. So in a way, like when we get to linkages, if two bodies are moving connected by a pin here, like in a way you could say, well, like it's easy to get confused and think like, oh, well, this body is fixed to that other body. That's sort of like a fixed point. But remember, the key is that that fixed point has to be fixed in an inertial coordinate system, which means it can't be accelerating. So if you have a pin connecting something to the ground, then that's a fixed point. If you have a pin connecting it to another body that's free to move, that's not a fixed point. Okay. So if it does have a fixed point, then A is the fixed point. If no, then the center of mass is the fixed point. No, then A is the center of mass. Now that you know what you're calculating things about, calculate the moment of inertia. If your about point is a fixed point, so in other words, if A isn't at the center of mass, then you have to use the parallel axis theorem. So yeah, if it does have a fixed point, and I suppose as long as that fixed point isn't at the center of mass, then you have to use the parallel axis theorem. So anytime you're calculating the moment of inertia about anything but the center of mass, you have to use the parallel axis theorem. Then the third step, draw the free body diagram. And if you miss this, I'll take points off on tests. Be sure you draw that, okay? This is kind of the same thing I said early on in statics, but free body diagrams seem unnecessary when you're working on simple problems. And, you know, in first semester dynamics, even our most complicated problems are fairly simple in the world of problems. But when you get into more complicated problems, it's really hard to get away without doing these well. And so that's just like a habit building thing for now. Okay, and then write out the table, pancake table. So pancake, artists, row 4, marzipan. Okay, now step 5, you can skip this if your about point is a fixed point. So skip if A is a fixed point. But if it's not, if you're doing it about the center of mass, then you have to use Newton's second law. So Newton's second law says add up all the forces, that's equal to the mass times the acceleration of the center of mass. If your about point is a fixed point, skip step 5. So you have to do it if your about point is the center of mass. You don't have to do it if your about point is a fixed point. And to get the forces for this, you're just adding up all the forces in the force column of the table. Step 6, rotational Newton's second law. So sum of the moments is equal to the moment of inertia about A times alpha. And for this one, you get all of the moments from the moment column of the table. So you can see where that table is helpful in these problems.
Table gives you moments.
It gives you the moments and the forces. It just has them all listed out right there.
Is that mass right there? That little one?
This is the mass, yep.
When you're talking about the angle, these are talking about the output.
Yes, that's right. And then the last step is You don't always have to do this. It depends what the problem's asking for. But if you're asked, or if you, for any reason, need the acceleration of a point on the body, use the watermelon equation. So the acceleration is equal to alpha cross r plus omega cross r. And if your about point is the center of mass, also use the relative motion equation that says acceleration of the pin relative to, or not the pin, the point, whatever point you're looking for, of the point relative to the ground is equal to the acceleration of the point relative to the center of mass plus the acceleration of the center of mass relative to the ground. Okay, so in the example I did, we sort of just felt our way through this rough approach without going through the steps, but I'll try to follow the steps in the examples I'm going to do. Yep.
So alpha is the same for all the objects.
That's right. So alpha and omega are properties of the body. Those don't change point to point, but accelerations, linear accelerations do. Everything. Yep. Yeah, just think of the body as having an alpha and an omega.
Say once you develop it, you can just pick any point in there and make it, and then it would have that saved.
Right. Yep, that's right. I mean, so really what that says is if you, if an object is spinning through space and you took a marker and drew a little line on a few different points on the body, that line would have the same angular motion at every one of those points. You know what I mean? Like if you had this big body and you drew a line here and a line here and a line here, and then just tracked this one and tracked this one and this one as this object spun around, those angles would change at the same rate, same acceleration and everything. But if you measured the translational acceleration of those 3 points, they'd be different. If A is the center of mass, so we saw it sort of so there are really two ways that it can come up. It can come up first because if you want to calculate the acceleration of a point on the body, then you're going to have to use the relative motion equation, and you're going to need it for the relative motion equation. This here is ACOM. And then the other way it comes in is if you're dealing with a fixed point or any unknown reaction force, then you're going to have to use Newton's second law. And then ACOM is going to have to come into it because the way those come in is that right? Yeah. So, yeah, I think there's two different ways that you're going to need to use the acceleration of the center of mass if your about point is the center of mass. Okay, let's, I guess let's take a break, come back right at 2, and I have another example or two to do, but we could also apply this method to practice problems if you want. So if anyone has any questions about kinetics practice problems, bring those and we'll work through them.